Hello everyone, so welcome to the next lecture, and this one is going to be a revision of important physics term. If you're confident with your physics, you may not need to listen to it, but it's always a good idea to do a bit of revision. So when we talk about radiometry, it is, well, we're basically measuring, talking about radiation, but what exactly do we mean by radiation? In this case, we're specifically talking about EMR, electromagnetic radiation, so not talking about alpha and beta radiation, we're talking about photons. So all EMRs are massless photons. And yes, you have a lot of different ones, right? You have your gamma rays, you have your UV, visible light, IR, and radio rays, but all of them are exactly the same thing. They are all photons, but they all do different things. They all behave very differently. So what are the difference between all these different radiations? Although the slide kind of gives it away. Now, before we go ahead any further, let's talk about which one would you rather be exposed to in the following context. A potentially dangerous ionizing radiation, like X-ray, for instance, but in a clinic, or pure wavelength light naturally found in sunlight, but a lot of it. Which one would you rather be exposed to? We'll come back to that in future lectures, but that's an important concept to think about. So the difference between X-ray, and in this case X-ray and visible light, is actually the amount of energy that's carried by each photon. X-ray carry more energies per photon than visible light. And the impact to that is that actually changes the frequency of the radiation. But the frequency of the radiation is well related to the velocity of the radiation and the wavelengths. The velocity of the wavelength is fixed at the speed of light. So meaning that if you change the frequency, you change the wavelengths, and you change the energy level of the photon. So you put the previous two formulas together, and you get this formula here. And what this is basically saying is that, well, with different radiation, they have different energy level per photon, but you can describe it using wavelengths, and which is how radiometrists and photometrists usually does it. We usually describe different radiation in terms of wavelengths. Note that other field might use frequency, but you just need to know that they are the opposite side of the same coin, courtesy of this formula. And yes, you will see this symbol everywhere. If you're Greek, that's the Greek letter for lambda. And that's the shorthand for wavelengths. So if I ever say lambda or show lambda on screen, just translate that into wavelengths. And yes, there are also kind of synonymous terms. Sometimes we refer to wavelengths as color if we're talking about visual visible spectrum, because color of a light is determined by the wavelength. So that's another important thing to remember. So what's the relationship between radiometry and photometry? Well, radiometry is handling any type of EMR. It doesn't really matter. It doesn't matter if it's X-rays, visible light, or radio wave. They all for radiometry handles all of them, and they're mostly concerned with energy. How much energy is being produced, transferred, or absorbed by other radiation? That is radiometry. It's a measurement of radiation, or specifically EMR. Photometry, on the other hand, is very, very narrow. It only talks about the visible light spectrum. It actually doesn't care about energy level. It only cares about how visible is the radiation. And that's the key difference between radiometry and photometry. I have a series of lectures about that. So remember, radiometry is just talking about energy, and photometry only really thinks about how visible the radiation is. It doesn't really care about the energy as much. But it does, but they're kind of related, only because they are related. So with the visible spectrum, so what is it? Well, typically it's giving out anywhere between 400 to 760 nanometer range. It's, as the name suggests, radiations that you can see with your eyes. Another important thing to remember is, yes, well, different wavelengths have different colors, but there is no single wavelength for white. White light is always a mixture of multiple wavelengths. We'll come back to it later. Yes, and wavelengths for visible light spectrum is usually measured in nanometers. But where does visible spectrum start and end? Actually, well, that's a good question. Let's just talk about UV first, which is shorter than visible light. UVA is the closest to visible light. UVC is the furthest from it, and therefore the shortest from it. Infrared, the scale goes the other way. A is the closest, and C is the furthest from visible light, but C is further from visible light, so it's going to be longer. It's going the other way, so it's a much longer wavelength. But it doesn't really answer the question, where does visible light start and end? Good question. Because where do you draw the line? Here is a lamp that emits UV light. I think it was, from memory, it's about, it releases mostly 360 to 380 nanometer light. So it's definitely in the UV range. But is it? But you can see, your eyes can still see UV radiations. So it actually, the strict defined range is 360 to 830, but in practical adequate range, typically they say 380 to 780. By industry access 400 to 700 nanometer, but as I just discussed, you can still see 360 nanometers. It's like, where do you draw the line, and why do you draw a line somewhere? It's not like your eyes can see down to 400 nanometer. As soon as you get to 399 nanometer, you can't see it. It doesn't work like that. It's a spectrum. So where and how and why do you draw this line? Well, it depends. It's ultimately arbitrary. It has really no true absolute meaning. We usually just choose a cutoff according to our purpose. Is what you want to remember. Yes, if it's relevant, your assignment, for instance, we will specify it. So that's it for the revision lecture. Next, we will start talking about radiometry.